Today we're going to talk about normalized cut, spectral clustering, and Shiger's inequality, although I think we'll leave the proof for next week. So last time what we talked about was clustering through the Laplacian. In particular, we talked about minimizing, right, over a set of vertices of a graph. And we asked for the set of nodes that we put on one side of the cluster to be exactly half of the number of nodes. Right, or let me use the formulation of cut. Right, we asked for something like this. This was minimum bisection. We saw that if we don't impose any kind of restriction on the size, then the optimal solution is just empty set or the set with everything. So in order not to do that, we just asked for the right. We asked for the set to be exactly even, and we saw that it had something to do with the spectral properties of the Laplacian, with eigenvalues and eigenvectors of it. What we're going to do now is going to be a little bit softer, right? So we will not want to allow the empty set or the set with everything, but also we don't want to force things to be exactly half the size. So one way to do this is through what's called the Shiger's cut. Right, and this is on your object Shiger, and this inequality, Shiger's inequality that we'll talk about. So Shiger cut is the following. You define this as the cut, but then to make sure that you don't cheat by picking just a set that's very small or a set that's very big, you divide by the minimum between the volume of the set and the volume of the set function. Right? So volume is like a better way of measuring size in this type of setting, right? Where different nodes get counted differently. Nodes with bigger degree get counted more. Right? So a volume of the set S is simply the sum over all I in S of degree. Right? It measures not only the edges that it cuts, but also the edges within the cluster twice now, right? In particular, it's not hard to see that, right, the volume of the whole graph is the same thing as the volume of S plus the volume of S. Right, so this way we're asking that the volumes are even. Right, and we're going to say things in terms of Shiger's cut, and Shiger's constant, right, of the graph is just the minimum over any subset of the nodes of the Shiger cut. Okay. So for now, we'll not study this one in particular. We'll study something very, very related, known as normalized cut. Right? These are basically different ways of dealing with this issue. So normalized cut is essentially the same thing. Instead, we take n cut of set S. Will be given by, you take the cut of S divided by the volume of S plus the cut of S complement divided by the volume of S complement. Right now, notice that, of course, cut of S and cut of S complement is the same thing. So this is exactly the same as just cut of S. Right? So basically, this is exactly the same as just saying that this is just cut of S 1 over volume of S plus 1 over volume of S complement. Right, in particular from this, it becomes completely obvious that this is very related to the Shiger's constant, right? Because if I have, right, this could be at most double, right? So I want to understand, say, the Shiger cut. Right, the Shiger cut is always smaller or equal than this. Because here I have one of them corresponds to Shiger cut, the biggest of these, because it's the minimum on the denominator. And it's always bigger or equal than half, because it picks up the minimum on the denominator, so the maximum number of n cut. So they're very related, right? In particular, of course, if I define n cut of a graph to be the minimum possible n cut I get, then clearly we have that the Shiger's cut the jiggers constant of the graph is between the end cut of the graph, half the end cut of the graph, and then. And so these things are two ways of normalizing that are, of course, very related. Okay, so we're going to now write things in terms of the normalized cut. So let's think about the normalized cut in a different way, right? So remember that we were asking that we're asking to minimize, right? Something like for some x, something like x transpose LG x. Right? The type of cuts we were finding were things that minimize, quadratic forms of the Laplacian. And we did so, first we asked sort of attempt one, was to ask that x is just plus or minus 1. And maybe balanced by saying that 1 transpose x was 0. Right? This is what we did last time. Now we're going to do something a little different. Right? We're going to be a little softer. We're going to say, well, we don't need it to be plus or minus 1. It just can take any two values. Right? For some fixed two values, it can take any of the two, as long as they don't take more than two values because we want to cluster into two things. Okay, so we're going to write a program we're going to say we're going to take x, or let me give you another name now, let's take y. Y is going to take values in either A or B, right? For some A and B. A and B, real numbers. And I'm going to ask to minimize this. Right, but now I ask it a goal, right? The goal would be to minimize, right, over such y as this. But I will also want, right, I'm assigning A to the things, say, in S, and B to the things outside of S, but I want to normalize them in some way, right? And so the way I'm going to normalize them is I'm going to use the volume. So the type of normalization I'm going to use is I'm going to say that, instead of just the sum of all the entries is 0, I'm going to do something very similar. I'm going to say that A times the volume of S, right? Because now I measure things with respect to volume, not just with respect to size, plus V times the volume of S is 0. Right? So I'm going to add constraints. And I also need scaling, right? Otherwise, I could just make double everything and there wouldn't be any problem. So I need some kind of scaling, right? The scaling is basically when I ask, right, here there are plus or minus 1s, but if I'm going to let A and B roam free, I need to scale them some way. So I need to bound, say what the sum of the squares is going to be. But again, we're doing things with respect to this volume, so I'm going to say that A squared volume of S plus B squared volume of S complement. Okay, this should be S complement, of course. S complement is and so I'm going to take these, I'm going to take the numbers to satisfy this. And of course, the goal being that y is going to be defined the following way. yi is going to be A if I is an S, and it's going to be B if I is not an S. Or is an S complement. That's the same thing. Right, and now this is sort of, right, this is almost like some sort of inner product of y, and this is some sort of norm of y. And actually, it's not just some sort of, right? What are we saying exactly? We're saying that, so let's look at what the constraints are. Let's say constraint exclamation points, constraint 2 exclamation points. Constraint exclamation point is simply saying that my y needs to satisfy, right, that the sum over I of yi degree of I needs to be equal to 0, right? Because if you think about what's happening here, yi will be A when I is in S, right? And so I'll get A times the sum of the degrees of the things in S, exactly the volume, plus B times the volume in S complement. So it's exactly this. And constraint double exclamation point is exactly the same thing, but with yi squared degree of I what is a more sort of spectral way of writing these constraints is just saying that up there, it's the same thing as saying 1 transpose dy equals 0. And the second one is just saying that y transpose dy equals 1. Right? These will be my constraints. Okay, so now we're going to try to explore what happens when we minimize subject to these constraints. Okay, so let's try to understand actually what y is. Right, so y needs to be of that form. Let's then try to understand what a and b need to be. Right, we can do some linear algebra. If we use the first one, and what do we get? We get that b needs to be equal to, right? So there's a minus a volume of s over volume of s complement. Right? So we get that. Then we also know that, right? What else do we learn? Well, we know that a squared, we know from 2, we know that this squared, so a squared, the minus goes away, volume of s squared, volume of s complement squared, times volume of s complement. Right? I'm doing the term in B first. Plus a squared times the volume of S. Right? This is 2. I reverse the order of the sum. This needs to be equal to 1. Okay, so what we get from here, we get that A, right? So let's work this out a little. 1 is equal to a squared times, okay, let's see what we got. We got 1s complement here, so we have volume of s squared over volume of s complement plus volume of s. If I did this right, we can take one of the volume of s's out, so I get equals a squared volume of s, and now we get 1 over, or now 1 is the same thing, right? 1 is the same thing as volume of s complement over volume of s complement. Okay, so let's go to this side. Okay, so we get that this is equivalent to and now what do I have? I'm going to rewrite this. I have volume of S over volume of S complement plus volume of S complement over volume of S complement. And now, right, the denominator is the same. And so I just get volume of S plus volume of S complement, but we know that that's just the volume of the graph. So really what we have is 1 is equal to a square volume of S, right, times volume of the graph over volume of S complement. So this means, of course, when we picked A and B, we didn't decide which one was going to be positive, which one was going to be negative. But let's say A is positive because we made S be the thing with the 1s before. So this means that A is just equal to big square root, right, of what we get here. We just have to divide the other thing. So we get volume of S complement over volume of S, volume of G. And now, if we go see what B is, because we had an equation for B, we get the following. Okay, so B was equal to that. So this means that B is equal to minus, right, A, so that times volume of S over volume of S complement. So we're going to multiply inside the square volume of S. So this shows up 2 volume of S is here. One of them cancels with this. 2 volume of S is complement here. One of them cancels with that. It's easy to see that what you get is volume of S over volume of S complement volume of G. And so what you have is that, if Y is going to be of this form, then Y actually needs to be of the following form. Y needs to be that it is of the type volume of S complement over volume if Y is an S, and the same thing with S and S complement flipped. Is not this. Okay, interesting. So now we can write specifically what this is, and now we can see what is Y transpose LG. Right, Y transpose LGY. Right. So now we can ask ourselves a little bit better. So now we can ask what is Y transpose LGY. Right? We know that this is the sum over all pairs of Wij, Yi minus Yj. Right? And where each pair only shows up once. But we also know that Y takes only 2 values, one in S and one in S complement. So only the pairs S and X complement show up. Right, so instead of indexing each pair by first I being the smallest and J being the bigger, I can just index it by Y being in S and J being in S complement. So this is the same thing as taking the sum over Y in S complement, Y and J in S complement, right? Every pair is showing up once, just like above. J times, right, nasty difference squared. Okay, let's see what this is. All right, so I get volume of S complement over volume of S volume of G square root minus also square root. Okay, so now let's expand this out a bit. I think for that I need the whole board. More water. Okay, so let's try and expand that out. So what do we have? We have, okay, so this is equal to, so Y transpose LGY is equal to, all right, sum Y in, okay, so we can expand, we can now simplify this a little, right? Because all these terms are exactly the same, right? So this is just cut of S times this sum. Right, because this sum doesn't depend on I and J, so we can definitely put just parentheses here. And this is just a cut of S. Okay, so this is equal to the cut of S times something. Let's see what that is. So there's terms here that, right, will have to expand, but the term of volume of G can come out. Right, and the term of volume of G comes out with square root, but then it has a square. So we can do one volume of G. And now what we have? We have the square of the first one. Volume of S complement times volume of S. Right? Minus twice the product of the two. Right? But what is the product of the two? I already took volume out. So they are, one you have S complement over S, and the other you have S over S complement. So you literally just get minus 2. Okay. Okay. Let's see if I remember the trick. Right, so we want the volume of G to show up on the numerator. So what we can do is take this 2. Is it on mine? There is a typo here that this is minus, this is the plus, right? Because A was equal to this, and B was equal to minus this, right? Because B had a minus sign. So when I take the minus, I need a plus. So this is a plus, sorry for the typo, okay. So now I need the volume to show up on the top to cancel with this one, right? So I can make a volume show up by taking one of these ones and making volume of S complement over volume of S complement. And, right, and we'll pick up a volume of G over there, and I can do the same over on that side. Okay, let's do this. So I get cut of S, volume of G. Now, I have volume S complement over volume of S. Plus, now one of these ones is going to give me a volume of S over volume of S. Another one of the ones is going to give me a volume of S complement over volume of S complement. And then I get volume of S over volume of S complement. Okay, now what do I have? Well, these have the same numerator, and this is just volume of G. Same thing for here. Right, so this will cancel with that one over here. And so really what I have is just cut of S, right? 1 over volume of S plus 1 over volume of S complement. Right? Not by accident, but this is exactly n cut for S. Yeah. So what did we just prove? We just proved that if we optimize that quadratic form, normalized in that way, and having, right, so let's do it. We just showed that if we now solve the minimum of Y transpose LG Y, such that Y takes only 2 values for some A and B. And that 1 transpose dy is 0, and 1 transpose, y transpose dy is 1, that the value of this is exactly, right, the value of this is exactly n cut of G, right? And moreover, that the solution is just to take S equals the entry xi where yi is A. Right? And this gives you S or S complement, of course. Okay, so now how do we transform it into a spectral problem? Right now we can do the exact same type of relaxation. Right? What we should be doing is now relaxing the condition that is this take 2 values. Because it already is normalized and it's already in, right? It already has this sort of orthogonality condition. Right, so now we can do exactly the same thing, right? We can relax Right? Exactly the same trick, and we relax the condition that this needs to take two values, and we go to something more spectrally looking. Right? So we minimize over y, satisfying y transpose dy, 1 transpose dy 0, y transpose dy equals to 1, y transpose LG1. But now we want to make this look a lot more like how it did before. Right? It's not quite yet there. So one thing we can do is we can take a new vector. We can take z, and use the other color. We can take z to be d square root. Right? This matrix is has diagonal elements all the negative, so I can take the square root of it. Right? It's just the square root of the decrease in the diagonal. And now I can say z d to the 1/2 y. And now what do I have? Let's rewrite this. Okay, with this change of variables, I have the following. I take the minimum. Right? Okay, maybe I should write what this means, right? It means that y is equal to d to the minus half z. So now I take the minimum of, right? So if you think about it, what you get is you still have a d to the 1/2 term. Right? This is the same thing as that. Now here you get exactly log of z squared, right? So it's starting to look a lot like a spectral thing. And here you get this thing, for now odd, but it won't be odd at all. So this matrix is known as the normalized Laplacian. There's many ways of normalizing the Laplacian. You can take just t minus on the other side. You can take just on this side. You can do it this way. If you think about it, it's a bit what we did in PageRank, right? When we normalized the weights that pages of importance that pages were given to others, it was a bit this that we were doing. Right? And so this is a normalized Laplacian. We define it as LG for the graphic. Right? And so now if you think about LG, right, it's again positive semi-definite, right? I mean, we're just multiplying two matrices, one on each side, right, in this way. So of course it's still positive semi-definite, right? Any z I put here, I can just think of this, right? Any z I put here clearly will be positive semi-definite because I can think of it as just this vector, and this was positive semi-definite, so it's still be positive. Now, if I think of LG, it's also not hard to see that, right, when z is d1/2 1, right, the d, let me write it this color, right, now the fact d1/2 1 is in the kernel, in the null space. Right? It's the eigenvector corresponding to the smallest eigenvalue. Right? Another way to say this is that LG times d1/2 1 is 0. Right? Of course, this is the case, right? Because if you think about LG, with d1/2 it cancels this one and gets a 1. We know LG times 1 is 0. So now with this extra ingredient, what we see, right? We see that we basically now already have a spectral problem, right? Because this spectral problem, that I'll write it again, right? The spectral problem of minimizing over Z with this condition. You're saying that you're minimizing this quadratic form, positive semi-definite matrix. Your vector needs to be orthogonal to the smallest eigenvector, the one in the kernel, and it needs to be normalized. The solution to this is exactly the second eigenvalue of the normalized Application. So this means in particular that we're immediately getting inequalities of the same type as before without having to be very brittle about things being exactly half the size. Right? We immediately get the inequality that lambda 2 of the Laplacian is smaller or equal than n cut. Right? This is So any inequality that comes completely for free. Right? And because we know that n cut is smaller or equal than 2 times the Cheeger constant, you immediately already get something else, which is you immediately already get that lambda 2 of LG is smaller or equal than twice times the Cheeger constant. This is known as the easy side of Cheeger's inequality. Now, how would we, okay, I'm going to erase just this part of the board and I'm going to keep the other two. And I'm going to switch color just to make it clear that this is the order of the boards is 1, 2, 3. How do we turn this into an algorithm? Right, we now compute, right, we can compute the minimizer of this, right, V2, right, the eigenvector of LG associated with lambda 2, right? We can definitely do that. And now, how do we relax, right? So we compute V2, this is our Z, then we can compute sort of a Y, right, or Y hat, an estimator for Y, think of it as some, right? For now, I take Y, some Y hat, to be D minus half V2, right? It should be sort of an approximation or a surrogate for my real Y. Right, now this is a vector for now sort of all over the place. If it only had 2 values, A and B, then I would be done. So right, a reasonable strategy right, is the following. Is you now grab this Y hat. This Y hat actually has a name. We usually call it phi2. Right, it's the eigenvector normalized in this way. We usually call it phi2. So a reasonable strategy is you take phi2, and now you threshold it. You try to threshold it. So pick a threshold. Tau. And now you say, I'm going to make S. Right? You indexed it with tau because for each tau you get a different S. Such that phi2 I is bigger than tau. Right, so in the picture, what are we doing? We're saying, think of the real line, take now the values of phi2, right? So maybe this is phi2 of 1, this is phi2 of 2, phi2 of 3, and so on and so forth. And you're saying, I'm going to pick a threshold, tau, and I'm going to make this S and this S complement. Now, what is the right threshold, right? Well, it's actually, you can just try all of them, right? Because there's essentially only n different possibilities for the threshold, right? So now just simply try all thresholds. And what we defined here is exactly spectral clustering. Right, so here we just define spectral clustering. We just derive where you take threshold, basically the algorithm is threshold or round phi2, the eigenvector computed in this way. Now, of course, the spectral clustering works for many dimensions, for any number of clusters, right? So what if we want the cluster in K clusters? if you want to take in K clusters, basically what we're going to do is we won't describe this in much detail in the course, but essentially what you can do is instead of taking phi 2, you take phi 2 and all the vectors up to phi k. Right, so you're going to take more eigenvectors of the Laplacian. Turns out that if you want to cluster in more sets, essentially it's the same as optimizing over not just the y, but many others are orthogonal, right? Think of the indicator vectors in each one of the sets, right? They're all orthogonal. And so you're going to take phi 2 through phi k, and now to a node I, right? So to vertex I, right? You're gonna add, okay, so let's say, right, what do I mean? Right? For each node I, associate with a vector in k minus 1 dimensions, which is phi 2, the entry I, phi 3, the entry I, and so on, phi k, the entry I. Now this is in, right, k minus 1 dimensions, but it's in Euclidean space in k minus 1 dimensions. And now the idea is you do k-means here. Right? Do k-means and these points. And if you think about what k-means is in 1 dimension, is exactly this, right? You find a center here, and you split in the middle. Split in the middle, right? So now think about what's happening, right? Like there's a lot more hidden here than what I'm saying, if you think about it. Because I had graphs, I had maybe some weird data in some like entangled way, and I built a graph, or maybe I started with a graph and I'm starting to cluster. And I'm saying that what you should do is embed the data in k minus 1 dimensions, right? In this particular way, using the eigenvectors. And then from there, from these eigenvectors, after embedding, you just do k-means. So what this is suggesting is if you understand the geometry of the graph, it looks nicely Euclidean space when it's embedded this way. So this is motivating something much more than clustering. It's motivating nonlinear embeddings of data, embeddings of graphs, and this will be exactly what we're going to do. Maybe next one we're going to prove Chig's inequality, but the one after we're going to start talking about diffusion maps, which is exactly ways of embedding graphs into Euclidean space, and will be precisely this, and we'll justify why this makes sense. Okay, so Chig's inequality is a way to argue that thresholding actually works. And we're going to do that next, and then afterwards we move into diffusion maps and nonlinear embeddings of data. Think of it as some kind of nonlinear PCA. Thank you.